So we're here trying to figure out how to test a completely general reduction of an X matrix to a matrix which spans a subset of the space which the X matrix spans. So the X matrix spans some space or other within Rn, and when we estimate the parameter vector of unknown parameters, what we do is we project our data, our y vector, which lies somewhere in Rn, we project it onto the plane spanned by the X matrix, and we get a beta hat, or rather an X beta hat as our prediction or estimate of the mean of y, predictor of y. Correspondingly, if we had assumed that our z was the correct representation, that we could in fact drop some of the X variables and should use z instead, then again, this is a subspace of Rn, but it's also a subspace of V, and we would then get a z gamma hat as the prediction, and we would now be interested in whether the new error from y to z gamma hat is too large when compared to the base model, which is this sum squared or error vector compared to the full model. So we look at x, the x as the full model, describing the full model, and then we look at the c as the reduced model. So the sum of squared errors under the reduced models are exactly this thing. They are the norm of y minus z gamma hat, whereas the squared, whereas the SSE, so this is SSE, which we would call SSE under the reduced model. And then SSE under the full model, we sometimes just call SSE, sometimes SSE under the full model. And that's going to be our y minus x b or beta hat. Now, it depends a little bit what exactly we're talking about, whether we use b's, should be using b's or beta hats. If this y is just a set of numbers, then we should be using b. If this y is a random variable, then we should use a beta hat. Now, of course, we shouldn't use b and beta hat in the same picture, but that's some artifact of something or other. So anyway, let's just change both of them to beta hat. So we think of this y now as a random variable in n-dimensional space, and the projection as a projection onto a subspace. And then we have a subspace of that again with z gamma hat. So we just put the hats on all of these and think of these as random variables. And that's our geometric description. Now to take this one step further, what we want to do is we want to somehow describe this in terms of orthogonal spaces. So we want to look at the projection onto V as a projection onto a space which is spanned by certain variables. So what we need to do is we need to find a set U1 through UR, which is such that this collection spans exactly the same space as the image of the projection with X, and correspondingly we would like to start that by spanning the Z space with the first of these variables. So we want to use some up to UR here, and then we want to go up to UQ here, where of course Q has to be less than equal to R, because the Z space is a subspace of area. So let's see how we do this. Move on a little bit. What we're going to do is we're going to write we're going to span, in other words, the C space with these first U's, and so we have U1 through UQ, and we can then write C gamma hat as a linear combination of the first U's. And remember how we project onto this. We know this is possible because we assume that Q is the rank of Z, so it is a two-dimensional space. So we can indeed find these U's, and all we need to do is we simply say, okay, let's see now, we have a Z gamma hat, which is the projection. If we take an inner product between that and one of these U's, let's say U1, then we know that this is going to be Z1 U1 plus up to Z hat Q times UQ, inner product U1. Now, since we have an orthonormal basis from Gram-Schmidt or whatever to space, this U1 to UQ from one orthonormal basis, this inner product here is going to be 0 for all of them except this one vector. So this is going to be Z1 hat U1 inner product U1, but U1 is a vector of length 1. That's what we mean by an orthonormal basis. So this is simply C1 zeta 1 hat. So zeta 1 hat is obtained by taking the inner product of U1 with this vector here. And that's how we obtain all the zeta hats. So that was easy. We do the same with the x's and the same with the y. And since x lies in a larger space, we need more vectors. And if we do this in the same way as we did in an earlier lecture, we just use Gram-Schmidt first to generate the basis for the C matrix. Then we expand it by continuing Gram-Schmidt with the columns of the X matrix. We will have these vectors first spanning the W, and then we will expand it with new variables, which expand the V. Then we continue with the unit vectors of Rn, and we get the rest. So we expand these bases from Q variables to R variables up to N vectors. Sorry. Now, the only thing we have not done is to investigate a little bit more closely exactly why these C's happen to be the same in all cases, and we haven't looked at the distributional properties of the C's. So let's stop here with this presentation. We now know that we have a basis which does exactly this. Our next step is to investigate why are these the same, and also to investigate the distributional properties if we put some distributional assumptions on the y. Remember, we get this result without any distributional properties of